Section 1. Introduction. We originally set out with the goal of finding a multiplicative theory of rings that resembled Z. I loosely described this by saying that every non-zero element of Z could be written as a unit times a finite product of primes. The units in Z are plus or minus 1, and the primes are 2, 3, 5, 7, 11, and so on. We've now seen a couple more examples. For example, in Z adjoin I, the units are plus or minus 1 and plus or minus I, and the primes are 1 plus I, 3, 2 minus I, 2 plus I, 7, 11, 2 minus 3i, 2 plus 3i, and so on. Remember that 2 is the square of 1 plus I, at least up to units, so we said that 2 was ramified. 5 equals 2 minus I times 2 plus I, and 13 equals 2 minus 3i times 2 plus 3i, so we said that 5 and 13 split in Z adjoin I. And 3, 7 and 11 remained prime, so we called these inert in Z adjoin I. Now, if I've done my job, you should already be convinced that it's inherently interesting to know what the units and primes in rings like this are. And we've discussed units at length now, so in this video we'll start looking more closely at primes in Dedekind domains like this. But first, just in case you're not convinced that this is interesting, let me give you another reason to care. We saw in video 5, and I reminded you at the end of video 9, that for odd primes p, minus 1 was the square mod p precisely when p split in Z adjoin I. Try it. Minus 1 is 2 squared mod 5, it's 5 squared mod 13, it's 4 squared mod 17, and so on. But if we write out the table of squares mod 11, say, we can see that minus 1 never appears, and we can do the same for all the other inert primes too. So minus 1 is not a square modulo the inert primes. So it seems as though the splitting of a prime in Zi has something to do with squares modulo that prime. This isn't a coincidence, but before we can explore it fully, we have to lay the groundwork. Section 2. Modular arithmetic. I deliberately assumed at the start of this course that my viewers only knew the very basics of modular arithmetic, how to add, subtract and multiply modulo m. So now let me spend a minute on an algebraic detour to ask, what about division? Well, I claim that division by n modulo m makes sense, that is, there exists some integer s such that n times s equals 1 mod m, if and only if the greatest common divisor of m and n is 1. And when this is the case, we'll usually call s the inverse of n mod m, and we'll write it as 1 over n or as n to the minus 1, adopting the more usual division notation. But notice that these things are integers. Here's a sketch proof of that claim. I'll leave all the details for you to check. In one direction, if the greatest common divisor of m and n is 1, then by Bezout's lemma, see video 1 for a reminder of that, there exist integers r and s such that mr plus ns equals 1. This implies ns is 1 modulo m. In the other direction, if the greatest common divisor of m and n is not 1, let's call it f, say m is m prime times f and n is n prime times f, notice that m prime is some integer between 1 and m minus 1. Now, m prime times n, that's m prime times f times n prime, and we can regroup that f with the m prime to see that this is just m times n prime. This is a multiple of m. So we have m prime times n equals 0 mod m. But now if n has an inverse mod m, then we can just multiply both sides by it. This gives us that m prime equals 0 mod m. This is a contradiction. In particular, when p is prime, division by n modulo p makes sense for all n between 1 and p minus 1. Here's an example. I'll draw out the multiplication table modulo 5, and notice that there is a 1 in each row apart from the 0 row. We can't divide by 0. For example, this 1 here says that 2 times 3 equals 1, or in other words, 1 divided by 2 equals 3. Division by 2 is multiplication by 3 modulo 5. We'll use this implicitly from now on, and we'll build on it in future videos. For now, here's a useful corollary. Let p be a rational prime, And let's consider expanding the expression a plus b to the p. By the binomial theorem, this is a to the p plus p choose 1 a to the p minus 1b plus p choose 2 a to the p minus 2b squared, and so on, up to p choose p minus 1 a b to the p minus 1 plus b to the p, where these coefficients p choose I, for I between 1 and p minus 1, are p factorial divided by p minus I factorial I factorial. I'll rewrite that by taking out a factor of p from the top. This is p times p minus 1 factorial over p minus I factorial I factorial. So now let me rewrite this binomial expansion. And I'm going to take out a factor of p from all these middle terms. I've been a little vague about what a and b are so far, so let me just say this for now. I want to take this whole expression modulo p, so when I write this out as a fraction, I don't want any factors of p in the denominators. And as long as that's the case, it makes sense to reduce this whole expression modulo p. When I do that, this factor of p here becomes 0, so all of these middle terms become 0. So, for any rational prime p, a plus b to the p is just equal to a to the p plus b to the p mod p, as long as the denominators of a and b don't affect that factor of p. Now in practice, if we take a and b to be elements of rings like Z, or Z adjoin root 2, or Z adjoin I, or rings like that, there's nothing to worry about. There are no denominators at all in these rings. On the other hand, if we ever find ourselves talking about rings like Z adjoin a fifth, we'll err on the side of caution and just completely avoid working modulo 5. From now on, I'm not going to mention this again unless it becomes an issue. Section 3. Primes of Z adjoin root 2 and squares modulo p. Let's take Z adjoin root 2 as the example. Z adjoin root 2 is a unique factorization domain, so we don't have to deal with ideals. We can just work with prime elements. As always, we can find all the prime elements of Z adjoin root 2 by simply factorizing all the primes of Z inside Z adjoin root 2. Now, if you believed the diagram of log space that I showed you in video 7b, you know that we can read off some information from there already. In that video, we mentioned that 2 ramifies, 3 is inert, 7 splits, and so on. But what if we didn't have that diagram? Well, it's easy to see where the ramification of 2 comes from. So let's take 3 as an example. The norm of x plus y root 2 is x squared minus 2y squared, and the norm of 3, therefore, is 9. So if 3 splits or ramifies in Z adjoin root 2, in other words, if it factorizes further, it must be a product of 2 elements of norm plus or minus 3, say alpha times beta, because the norm function is multiplicative. In fact, if there's any element alpha of norm 3, say alpha is x plus y root 2, then let's set beta equals x minus y root 2. It's root 2 conjugate. Right, then alpha times beta, which is the norm of alpha, is equal to 3. So 3 does factorize as alpha times beta. And if there's an element alpha of norm minus 3, then we can just multiply it by an element of norm minus 1. For example, one of the fundamental units for Z adjoin root 2 that we found in videos 7 and 8, say 1 plus root 2. Then 1 plus root 2 times alpha has norm 3, and we're back in the above case. So 3 factorizes here too. Conversely, if there are no elements of norm plus or minus 3 in this ring, 3 won't factorize non-trivially. If alpha times beta equals 3, which has norm 9, and there are no elements of norm plus or minus 3, then one of alpha or beta must have norm plus or minus 1, which makes it a unit. So 3 must remain inert. So this is an if and only if statement. 3 factorizes if and only if there are integers x and y, such that x squared minus 2y squared equals plus or minus 3. So that's how we'll approach this question. Do such integers exist? I'm going to show that they don't. Firstly, we can rule out the case where 3 divides y. If 3 divides y, then x squared is a multiple of 3, and by Euclid's lemma, that means that x is a multiple of 3. So x squared and y squared are actually divisible by 9. Now, mod 9, the equation x squared minus 2y squared equals plus or minus 3, reduces to 0 equals plus or minus 3. That can't happen. So now we know that 3 doesn't divide y. Let's reduce mod 3, so that we have, for some integers x and y, that x squared minus 2y squared equals 0, or in other words, x squared equals 2y squared. Now we can divide both sides modulo 3 by y squared, because of the earlier section on modular arithmetic. We get x over y squared equals 2 mod 3, and we can take this number x over y to be an integer, say z squared equals 2 mod 3. But by writing out the squares modulo 3, we see that this is impossible, so 3 must be inert. In fact, this argument applies more generally. I'm going to go through this argument, replacing all instances of 3 with p for some rational prime p. The element p factorizes in z adjoin root 2, if and only if there are integers x and y such that x squared minus 2y squared equals plus or minus p. If p divides y, then both x and y are multiples of p squared, so we get 0 is plus or minus p mod p squared, a contradiction. So we can reduce mod p to show the existence of x and y such that x squared equals 2y squared mod p. And since p doesn't divide y, we can divide through by y squared to get x over y squared equals 2 mod p, or in other words, z squared equals 2 mod p for some integer z. So, what we've shown is if p factorizes further in z adjoin root 2, then 2 must be the square of some integer modulo p. So for example, if we write out the squares modulo 11, we find that 2 isn't there, then we can conclude that 11 doesn't factorize in z adjoin root 2. But if we write out the squares modulo 17 and we find that 2 is there, can we conclude that 17 does factorize in z adjoin root 2? In other words, is this argument reversible? Surprisingly, yes it is. Suppose that z squared equals 2 mod p for some integer z, that is, 0 equals z squared minus 2 mod p. So p times n equals z squared minus 2 for some integer n. Factorizing the right-hand side inside z adjoin root 2, it becomes z minus root 2 times z plus root 2. And because z adjoin root 2 is a unique factorization domain, it has an analogue of Euclid's lemma. If p is a prime element of z adjoin root 2, then it must divide one of the two factors on the right-hand side. But that can't be true. If I divide z plus or minus root 2 by p, I get z over p plus or minus 1 over p root 2. This definitely isn't in z adjoin root 2 because, for example, this isn't an integer. This is a contradiction. So p can't be a prime element in z adjoin root 2, and so it can be factorized further. Say, p equals alpha times beta, where neither of alpha and beta is a unit. So now we're done. In summary, the prime p factorizes further in z adjoin root 2, if and only if there exist integers x and y such that x squared minus 2y squared equals plus or minus p, and we've seen that this happens if and only if 2 is a square mod p, that is, if there is some integer z such that z squared equals 2 mod p. So, given that 6 squared equals 2 mod 17, we know that 17 does factorize further in z adjoin root 2. This has simplified our problem a lot. If we want to check whether any given prime p factorizes further in z adjoin root 2, we only have to write out the squares mod p. But that might still be hard to carry out in practice, for example, if p is large or we want to check lots of primes. In z adjoin I, we were able to give a very simple characterization of when a prime factorized further and when it didn't. P factorizes in z adjoin I, if and only if there exist integers x and y such that x squared plus y squared equals p, which happens if and only if minus 1 is a square mod p. And an argument in video 5 using Euler's criterion told us that this happens precisely when p equals 2 when p ramifies, or p equals 1 mod 4 when p splits. This solves the question for all primes simultaneously, so can we find a result like this for z adjoin root 2? Section 4. Congruences. To fully understand how primes factorize in z adjoin root 2, we need to know the following. When is 2 a square mod p? So, let me remind you of Euler's criterion again. Provided p is an odd prime, the number a to the p minus 1 over 2 is congruent to 1 mod p if a is a square mod p, and is congruent to minus 1 mod p if a is not a square mod p. So, our aim is to calculate 2 to the p minus 1 over 2 mod p, which will be either plus 1 or minus 1, and we need to calculate this for every p. First, let's just multiply both sides of this by 2. We don't lose anything here. P is odd, so we can always just divide out by this mod p later if we want to. So we're calculating 2 to the p plus 1 over 2 mod p, which will be either plus 2 or minus 2. Okay, it seems natural to rewrite the expression on the left-hand side inside z adjoin root 2 as root 2 to the power p plus 1. Now here's the trick. Let zeta be e to the 2 pi I over 8. That's a primitive 8th root of unity. I'm going to draw zeta and the powers of zeta in the complex plane over here. Now zeta is 1 plus I over root 2, and zeta inverse is 1 minus I over root 2, so their sum is root 2. Let's substitute that into this expression up here. We get zeta plus zeta inverse to the power of p plus 1, which is zeta plus zeta inverse to the p times zeta plus zeta inverse. Now, because we're considering this mod p, by the binomial expansion we derived earlier, this is just zeta to the p plus zeta to the minus p times root 2. Now, because the values of zeta to the n are periodic in n, that is, zeta to the 8 equals 1, so it repeats every 8, zeta to the n plus 8 is zeta to the n, it makes sense to separate this into cases modulo 8. For example, if p is 1 mod 8, then zeta to the p is just zeta to the 1 by subtracting off an appropriate multiple of 8. And likewise, zeta to the minus p is just zeta to the minus 1. So this expression here is 2. In other words, 2 is a square mod p. If p is minus 1 mod 8, then zeta to the p is zeta to the minus 1, and zeta to the minus p is zeta to the 1, and the same thing happens. On the other hand, if p is 3 or minus 3 mod 8, then zeta to the p plus zeta to the minus p is just zeta cubed plus zeta to the minus 3, which we can calculate or read off from our diagram, is minus root 2. So in these cases, this expression is minus 2. So 2 is not a square in these cases. Section 5. Splitting versus ramification. We now know that if p is 3 or minus 3 mod 8, p is inert in z adjoin root 2. And if p is 1 or minus 1 mod 8, then p factorizes further in z adjoin root 2 somehow. But we've identified two kinds of factorization: splitting, a product of two different primes, and ramification, the square of a prime up to units. Which one is it? Well, if p is 1 or minus 1 mod 8, then p can be written as the product of two conjugate elements of norm p. Say x minus y root 2 and x plus y root 2. And remember from before that both x and y must be co-prime to p. So let's calculate their greatest common divisor. If they share some prime factor in z adjoin root 2, say pi, then since pi divides them both, it must divide their sum and their product. Their sum is 2x and their product is p. So pi divides p, and by Euclid's lemma it divides either 2 or x. Well, we've already ruled out x because x is co-prime to p. So the only possibility is p equals 2. But that's not plus or minus 1 mod 8. In other words, x minus y root 2 and x plus y root 2 have no common factors in z adjoin root 2, so they're not just unit multiples of each other. So p genuinely splits into a product of two distinct primes inside z adjoin root 2. Now, we excluded p equals 2 from the conversation a long time ago, but for completeness, let's just remark that we already know that 2 ramifies in z adjoin root 2. It's just the square of the prime element, root 2. Section 6. Next steps. This investigation raises lots of questions. Firstly, what about other unique factorization domains? The only part of this argument that doesn't immediately seem to generalise, so that we can apply it to, say, z adjoining root 3, is the calculation in the middle involving zeta, the 8th root of unity. Zeta seem to have a natural relation to root 2 already, whereas we might need to find an entirely different way of approaching the problem for different rings. Secondly, what about non-unique factorization domains? All the way back in video 2, I remarked that z adjoining root minus 5 was not a UFD. But then in video 3, I gave a set of congruences that determined when a prime ideal of z split remained inert or ramified after being extended to z adjoining root 5. So where did that come from? Thirdly, I was quite vague about how congruences worked in this video. What does it mean to work, say, mod 2 or 3 or 5 or 7 inside z adjoining root 2? You might have noticed that in the crucial calculation in section 4, we were working inside the ring z adjoining zeta, where zeta was equal to 1 plus I over root 2. In other words, there was already a factor of 2 floating around in the denominators. Now this didn't matter because we'd already excluded the prime 2 from consideration, but how can we be more careful about this in future? Finally, throughout this series we've mostly worked inside rank 2 extensions, that is, quadratic extensions of z so far. But we can't stay there forever. In the middle of this calculation we were led to consider the arithmetic of z adjoining zeta, which is rank 4 as an extension of z. What does the arithmetic of this ring look like?